Introduction to Organic Chemistry. For this session, we're going to have 3 objectives. The first one, describe the atomic structure of carbon, explain how the structure of carbon atom affects the type of bond it forms. And third, recognize how carbon atom forms different kinds of compounds with other elements in itself. Okay, take a look at these pictures. What can you say about it? How does it feel when you taste or you smell these kinds of food? They may smell sour, like sweet, and also the chili would be very, very spicy. Yes, so as you have known, all these sensory experiences that we got from these kinds of food are caused by special compounds, and these special compounds are very abundant in our environment, not just in our food, not just in our clothes, not just in the things that we see around, but also in our very bodies. Okay, what comes into your mind when you hear the word organic? Ever heard of the word organic? Like organic food, organic matter, organic compound. Okay, how about in these pictures? Which of these are organic? And which of these are not organic? Okay, if you got the answers right, the organic substances are sugar, this duck, the cow, the corn, the banana, the rose, the berry, the house material, the plant, except for the stone. We will see why. Okay. When we talk about the word organic, it can mean different things. To the lay people, the word organic would mean organic fertilizers or organic in the original sense, from living organisms, organic food, those foods that are grown without synthetic fertilizers or pesticides. All these kinds of food. Look at that, organic. But to the chemist, these words matter differently. Organic depicts compounds that contain carbon and other elements such as hydrogen, oxygen, nitrogen, phosphorus, and sulfur. It's talking about this composition. For example, this kind of compound. Alright. In this subject, we're focusing on a branch of chemistry, which is organic chemistry. This is the study of compounds that contain carbon. Technically, compounds that contain carbon. It is one of the major branches of chemistry, a field of study that greatly contributes to the production of the consumer products we buy and use every day. Look at these kinds of figures. These are some examples of organic compounds. We can have this kinds of skeleton figures, this one, or we can have ball and stick. So these are types of models that the chemists have agreed to show organic compounds' molecular structure. Another terminology in chemistry is this difference between organic and inorganic compounds. When we say organic, it is having that bonds which are entirely covalent, and inorganic, the bonds are ionic. Ever remember about these two words, ionic and covalent? Alright, when we say covalent bonding, there is a sharing of electrons. This usually happens among nonmetals because they tend to gain electrons. When we say ionic, this happens mostly on metallic substances, which usually lose electrons. And as they lose electrons, there is a transfer instead. It's not sharing, but transfer. For organic, look at this image. This moving image, the yellow small ones are the electrons. The red one, it's the oxygen atom, and the white one, it's the hydrogen. Would you look at that? Small yellow dots here come around oxygen, and it's like they're sharing the electron from hydrogen. So it is a sharing relationship. For this second one, look. Sodium has one electron. And this tiny electron is shared into the orbits of chlorine. And they still become bonded together. But this time, there's a transfer of electrons. That is a type of an inorganic compound. So, sodium chloride is an inorganic compound, whereas water, not really organic. Well, those are examples of the type of sharing in ionic and covalent bonds. When we say organic, they have covalent bonds. Inorganic, ionic bonding. These words bonding are types of chemical bonding that happen among atoms. Okay, let's proceed. But there will always be exceptions to the rule. Not all compounds that contain carbon will be considered as organic. Some are considered as inorganic. And these are the exceptions. Number 1, oxides. Number 2, ionic compounds of carbon-based ions. For oxide, the first one, it's carbon monoxide. Number 2, it's the carbon dioxide. Just a little things to remember. Number two, the carbonates, cyanides, carbide ions, such as silicon carbide. Okay, special things. Okay, people before thought that organic compounds or compounds that contain carbon are just exclusive for living organisms, and we can't create them. We can't produce them or manufacture them. But this was disproven by a single experiment by Mr. Friedrich Wöhler. He synthesized the urea in the lab and proved that organic compounds can be made without the involvement of a life process. Okay, what did he do? He had a mixture of ammonium chloride and silver cyanate and heated it. This is a symbol for heat, and it became urea. Urea with a white substance. Some silver chloride exists, and this is the molecular structure. Nobody thought it would ever be created in the lab, and that is why organic compounds can still be and that is why we can say that organic compounds can be created in the lab. It's not just exclusive to living things. Okay, look at this pie graph. Can you find carbon? Where is it? It would be hard to look at it because it belongs around here. Just a tiny bit. Oxygen and silicon are majorly abundant in the Earth's crust. These elements usually constitute the elements inside stones and rocks. So, because our Earth is a rocky planet, but this tiny carbon that's found here is the very essence of life, and that is why it's called the element of life. Okay. It is so small, but why is it so special? Just why? As we have observed, a lot of compounds around us are made up of organic compounds. 90% of the compounds are organic. All those products that we use, they're organic substances. Again, organic, the technical organic, containing carbon. Okay, why are there so many organic compounds on Earth? Okay, before we dive in, let's get familiar first with our tools. Scientists have designed and have agreed on this rigid set of rules on how to view these molecules and how to represent these molecules, and these are what they call the structural formulas. We can have it presented in a ball and stick model, an electron dot formula, these are dots of electrons, or a dash formula, or a condensed formula, or a bond line formula. In a bond line formula, each vertex are considered as carbon, and the ends here is also a carbon, and the H are not shown. It's as simple as that. Okay, let's look at the three familiar ones. The structural formula or the dash line formula, they're both similar in name. These are the stick figures that you have seen so far. For example, we have carbon, 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 and connected by hydrogens. This is a kind of a dash formula, wherein you can see dashes surrounding atoms. The number of dashes will be depending on the bonding capacity of that atom, and we will learn later about the bonding properties of carbon. The Louis dot structure is this kind of representation wherein the valence electrons are shown around the element. You still remember about the planetary model from Niels Bohr? How many electrons does carbon have? We have, looking at the periodic table, there are 6 electrons. And how do we draw its arrangement inside the orbits? We have the capacity of 2 here, remember? And here, we have the capacity to hold 8 in the second shell, remember? But if you don't remember, you can really review. The formula for this one is 2n squared. Okay, because it's 6 and there are already 2, you can have 4 sitting in here. That means there are 4 on its outermost shell. I just didn't continue the circle, but it's supposed to be a circle on this one too. Okay, so the 4 are what you call the valence electrons. Valence electrons are the electrons in the outermost shell. Okay, how about condensed formula? Looking at this structure that we draw in number 1, condensed formula is that condensed version without the dashes, and the H's are written around a single C. For example, the first C, this one, there are 3 H's around it, so you just write CH3. And then the second C, there are 2, so CH2. And this one, CH3. So it is understood that it is written in this order. Structural formula shows arrangement. This one, order. But sometimes it can still be written in another kind of formula that we call empirical formula, or the simplest form. This is the most condensed form. So how many carbons are here? 3. So just write 3. And how many H? This is 6, 8. C3H8. Okay, this is another kind of writing. Just remember this 4. The structural, Louis dot structure, condensed, and empirical formula. Alright, let's go to the star of this lesson, the atom carbon. Carbon is considered as the element of life. As I've already mentioned a while ago, there are 4 valence electrons surrounding it. There are 4 valence electrons on the outermost shell. It has 6 electrons, 6 protons, and 6 neutrons. The mass of 12 gram per mole. The atomic number of carbon is so versatile that it can make long branches of compounds and different varieties. And the reason is its bonding properties. It's so unique that carbon can, number 1, it can create 3 types of bonds. 3 types of bonds. The first one, a single bond. When we say single, just 1, double, 2, triple, 3. Look at these pictures. One lines around. So within a C, one carbon to carbon, there is one bond. Carbon to another atom, you can make 2, and you can make also 3. In a single bond, one pair of electrons is shared between 2 atoms. When we say shared, they're sharing it. So both has it. And for this one, carbon has an electron here, and hydrogen has an electron here. And 2 pairs, meaning they're sharing 2 per pair. So let's just have a shortcut. So let's draw first the Lewis structure of carbon. There are 4 dots around it. This is the Lewis structure of carbon. 4 valence electrons are shown. This carbon meets a hydrogen that has 1 electron, because hydrogen is the first element that has an atomic number of 1 and has just 1 electron as well. And they tend to share this one. As mentioned a while ago, there are 2 and there are 3. Elements try to follow this octet rule. Octet rule, wherein the outermost shell must be fully 8. So because it's 4, it needs 4 more. So it looks for other elements to bond with so that it will be stable. This is for stability. The exception for this one is hydrogen, because it can only hold 2. Okay, just remember that. Going back to C. So C is looking for 4 more. Here, it finds 1 hydrogen, and the hydrogen is good enough to share its electron, and these other electrons too would like to look for other elements, and hopefully another hydrogen comes, and they share these 2, and another hydrogen, and another hydrogen, and they share these 2. And these are those sharing bonds or covalent bonds. That means there are 4 more electrons that are being shared. And if you count them all, that would be 8. And when it's 8, it becomes happy because it's satisfied with the octet rule. So this is a single bond. How about a double bond? A C having 4 valence electrons could meet another carbon which has 4 valence electrons. It has the capacity to form a covalent bond here, share these, and another covalent bond here. This is a double bond. So these 2 here would look for other elements to bond with, for example, hydrogen. And this one, hydrogen. This is an electron. This one, hydrogen. And this one, hydrogen. Pardon my drawing. So to write that better, you can write C, 1, 2. Okay, and maybe some 2 lines here. Sometimes they're written in angles, sometimes they're written in straight lines only. Both are accepted. 1 up or down or up or side. All are accepted. You can have all. Or like this. Up or down. Up or down. There's an H here. Like that. How about a triple bond? So C having 4 could meet another carbon and could share these 2 here, and share these 2 here, and share these 2 here. And this one goes looking for other elements to bond with, say other carbon, or maybe other electron, other hydrogen. Let's do it again because it's erased. Okay, this, you can have another element here, maybe another carbon here, and so on. But can you make 4? Can you combine these 2 and these 2? No, it's not possible, because the structure of the carbon inside its molecules, it really just allows for up to 3. Up to triple bond only. Just remember that. Okay, in summary, carbon can hold 4 bonds at maximum, but 4 bonds, 4 single bonds. But with carbon to carbon, it can only have a maximum of 3. Okay, only 3. Not so much. Okay, kutob lang o 3. Let's go next. So having these 3 types of bonds, we also have their characteristics. Observe the numbers. 153.5 picometers, 133.9 picometers. Picometers. 120.3 picometers. Yes, picometers. Okay, it becomes shorter, right? Shorter. It gets shorter and more bonds are here now. 3, 2, yes. So as you go from here to here, it becomes shorter. But actually, it also becomes stronger. It would be harder to cut these bonds a lot more than having these two being cut out. So it's stronger and shorter, but shorter. Then another property is that carbon can make this kind of arrangement. So there are different kinds of arrangement of molecules. And this one is for single bonds. When carbon makes single bonds, full 4 single bonds, it tends to arrange in this kind of arrangement, a tetrahedron. So these 4 hydrogens are trying to stay as far as possible because they tend to repel each other because of these electrons that are present around them. But at the same time, this whole atom is holding itself. Amazing, right? Okay. Lastly, this amazing property of carbon carbon can connect with not just itself but also with other elements too. So you can have this. So look at that. The first level, these are the Lewis structures of different elements that can possibly combine with carbon to form organic compounds. So the first one, we know that carbon has 4 valence electrons, and nitrogen, how many electrons does nitrogen have? Nitrogen actually has 7, but because the 2 are on the first level, on the outside it's just a remainder of 5. So it has 5 valence electrons. Next, oxygen. How many electrons does oxygen have? And look at it in the periodic table. The atomic number that indicates the number of protons and the number of electrons. Oxygen has 8. So let's draw the planetary model again. It's always 2 in the first level and a maximum of 8 in the second. So 2 needs 6 more. 1, 2, 3, 4, 5, 6. Okay, so there are 1, 2, 3, 4, 5, 6 on the outside, 6 valence electrons. So when we draw the Lewis structure, it would be 1, 2, 3, 4, 5, 6. Like that. Next, hydrogen. Hydrogen is the first element in the listing of the periodic table. It just has 1 proton, 1 electron. That means it just has 1 electron sitting on its first energy level. Okay, and it's ready to share that very electron. It's very kind. Then X. How about this X? What element is X? Is it xenon? Is it? No. There it was written that it has 7 valence electrons. Looking at the periodic table, the halogens on the last part of the periodic table, the halogens, the fluorine, chlorine, bromine have their group number 7A. So these actually refer to the halogens. What are those halogens? We have fluorine. Erase again. Halogens. Those fluorine, chlorine, bromine, and iodine. Okay, so these have a remainder of 7 at its last shell. So it has 7, and it can only share. Now, let's look at their bonding capacities. Carbon has, just because they have these valence electrons, it doesn't mean that they can share all these. So for carbon, it can share all 4. So it makes 4. So it is possible for carbon to have 4. But nitrogen, even if it has more valence electrons, it can only share 3. So it's not always nga mahatag niya ang tanan. Okay? So para sa iyang self-run siyang 2. These 2 tiny electrons here nga dili ma-share, that is what you call lone pairs or unpaired electrons. Lone pair. It wants to be on their own. Di siya ganahan mag-share. So, nitrogen has a bonding capacity of only 2 with these 2 lone pairs that are imaginary. They want to have it their way. How about oxygen? Oxygen also has lone pairs and 2 pairs. This one and this one. It is able to share only 2. The 2 are around here. How about hydrogen? Well, hydrogen is so kind to share all that it got, so i-share niya ang tanan. And then this one, again, these are the fluorine, chlorine, bromine, iodine. Okay. It also has 3 that is not shared, and it only shares 1. Okay, accepted. Alright. Here's the summary. Carbon can form 4 covalent bonds, covalent to share, with no unshared pairs. 3 covalent bonds for nitrogen, with 1 unshared pair. 2 covalent bonds for oxygen and 2 unshared pairs. 1 covalent bond for hydrogen, no unshared pairs. And the halogen X, fluorine, chlorine, bromine, iodine, normally forms. So there are other situations nga dili pud sila mag-form og inani. But kasagaran lang kay 1 ra jud lang covalent bond with 3 unshared pairs of electrons. Review. You just have to remember these. Dali ra man sa ma-memorize. Carbon, it can make 4. Next, nitrogen. It can make, you can pause the video if you like, 3. How about hydrogen? It can make 1. By the way, you can write it this way or this way, whichever way. And this one too. Then how about oxygen? It can make 2. Or you can write it this way. Double bond, maybe a double bond or a single bond. Oxygen is capable of double bonds too. Remember this. So oxygen can make single bonds and double bonds. We're done. I think it's just the remaining fluorine. So if it's fluorine, it can make a single bond only. If it's chlorine, it can make a single bond. If it is bromine, it can make a single bond. And then if it's iodine, it can make a single bond. We will see later at the examples on how this bonding works.